Welcome back to Algebra 1 Honors. We are going to look at Lesson 11-8, Adding and Subtracting Radicals. Now, when you look at our problem here, it's not immediately obvious that we can combine anything here, because the only radicals that we can add together or subtract from each other are radicals which have the same number under the radical sign here, the same radicand. Okay? And 112, 56, and 126 are not the same. But radicals are kind of like fractions. And if you go back and you remember fractions, okay, fractions are like chameleons. We have all different kind of names for a particular fraction. Like 1/5, if I multiply the top and the bottom by 2, 1/5 is equal to 2/10. If I multiply by 3 on top and bottom, I get 3/15. So fractions are like chameleons, right? They have all different appearances for the same value. It's kind of like you can have a quarter, or you can have 2 dimes and a nickel. Same amount of money, same value, but different representation, right? So what we have to do when we want to add fractions is find the chameleon, or the appearance that's the same for the denominators. All right, so we take 1/5 and we multiply top and bottom by 4, and we get 4/20. Now that's another name for 1/5. Same value, but different name for it. Okay? And down here I multiply 1/4 by 5 over 5, and I get 5/20. Okay, well now I can actually add these two together, because the chameleons, in this case, have the same denominator, which is what's important in fractions. And I add them together and I get 9/20. Okay, so that's 5th grade stuff, 4th grade stuff. All right, but we have to do something similar when we add radicals or subtract radicals. We first have to make sure that we have simplified the radicals themselves, because we can't tell until they're simplified whether any of them can actually be combined. So we're going to look at this 112 and see if there are any perfect squares in 112. Well, I do that by taking my 112, and I'm going to use what Mr. Kiger calls the upside down method. I'm going to prime factor, find all the prime factors in 112 and see if there are any twins, any perfect squares. So I divide by 2. Start with 2 and I get 56. Do another 2 and I get 28. Another 2 and I get 14. Another 2 and I get 7. Okay, now I have a pair of 2's here, which would be 4, right, when I multiply them, and a pair of 2's here, which would be 4. Right? So I can break 112. Another name for 112, right? The square root of 112 is the square root of 16 times the square root of 7. And on your calculator or on your paper, you can multiply 16 by 7 and make sure we get 112. And then that 4 was our original 4 that was there. Okay? Now, let's go ahead and do that step on the next one, and then we'll come back and simplify. So if we come over here and we take 56, and we do the upside down cake method on 56, we start with 2, we get 28, divide by 2, we get 14, divide by 2, and we get 7. Okay, so 8 times 7, that's 56. Now, the only set of twins we have here is a 2 here and a 2 here. So, my new name for the square root of 56 there is going to be the square root of 4 times the square root of 14. And 4 times 14 is 56. And then we bring down our original 5 that was there. Okay? Now we're going to do the upside down cake on our last number there, 126. So we take 126, start with 2, okay, we get 63. Start with 2 again, we get, 2 doesn't work there, okay? So we have to do 3. We get 21. We can do 3 again, and we get 7. Right? Now, my only twins here are the 3's, my only perfect squares. So I'm going to break 126, square root of 126 up into the square root of 9 times the square root of 14, and then we'll bring down our minus 9 there. Okay, now, next step. What is the square root of 16 here? Well, that's 4. So now we have 4, our original 4, times the square root of 16, which is 4, times the square root of 7. That gives us 4 times 4, which is 16, times the square root of 7. Okay, that's one term simplified. Now, here, the square root of 4 is 2. So now we have 5 times 2 times the square root of 14. 5 times 2 gives us 10. 10 square root of 14. Okay, and the last one, minus the square root of 9 is 3. So we have 9 times 3 times the square root of 14. That's minus 9 times 3 is 27. Square root of 14. Now we've simplified, just like we did with finding the common denominators over here, we have simplified the numbers under our square root signs, they are under our radical sign. There aren't any more perfect squares in any of these numbers. Right? So they're as simple as we can get them. So now we can look at them and we can combine, okay? We can combine the ones that have the same number underneath here. Okay, so the only two that are combinable here that we can add together are this one and that one. Because this guy, he's got a square root of 7. He's a different animal. So our answer is going to have a square root of 7, 16 square root of 7 in it. And then positive 10 of these square root of 14s minus 27 of them is going to give me a minus 17 square root of 14. You keep the radical the same and you add the coefficients, the numbers that are in the front. Okay? But again, you can only combine when the number underneath your radical sign is the same. Okay? Now, if we had another square root of 7 out here, we could combine those two terms. Okay, but that's our answer. It's kind of odd looking, but that's as far as we can go. Now, if you needed an answer to the nearest tenth or the nearest hundredth, what you would do is take your calculator, punch in the square root of 7, punch 7 and then square root, multiply it by 16. You get some decimal number here. You do the same thing over here, and then you'd subtract, and that'd give you an estimate. Okay, not an exact answer, because this is what we call an irrational number. It doesn't have an exact decimal value. You could never find a decimal value for square root of 7 that either repeats or stops, terminates. It's irrational. Okay? Now let's look at 2 more problems. And this one kind of has the best of both worlds. It has fractions and radicals. So we have the square root of 2 over 7 minus the square root of 7 over 2. Now, because this is a minus, not a times, we cannot put these two under the same square root sign. Okay? Just cannot do that. And you can convince yourself of that if you want to try. Take the square root of 9 minus the square root of 4. and see that that's not equal to the square root of 9 minus 4. All right, square root of 9 is 3, minus square root of 4 is 2, that's 1. That does not equal the square root of 5. Okay, so don't be tempted to do that. We all are, but you cannot combine them there. All right, so what we want to do is, again, we want to get a common denominator here. Well, I look at 7 and 2, and my common denominator is 14. So if I multiply top and bottom here by 2 over 2, because that's multiplying by 1, that doesn't change the value, I get right here 4 over 14, and that's another name for 2 7s. Then over here, I'm going to multiply by 7 over 7, and I can do that because that's 1, and multiplying by 1 doesn't change the value. And I get minus the square root of 49 over 14. Okay? Now, then, when I have a fraction under a radical like this, I can, when it's divide like this, so I can break it up into square root of 4 over square root of 14. Okay? And over here, that's going to be square root of 49 over square root of 14. Well, I can simplify a little bit because the square root of 4 is 2. And the square root of 49 is 7. Okay? So now what we have 2 over the square root of 14 minus 7 over the square root of 14. Same denominators, kind of a strange looking denominator, but the same denominator. So we can combine the numerators and we get 2 minus 7 over the square root of 14. 2 minus 7 is negative 5 over the square root of 14. Now, we're almost done, okay? But just by convention, just because somebody defined it this way, we don't leave radicals in the denominators of fractions, okay? Why did they decide that? I don't know, okay? But in order to get rid of this square root in the denominator, we have to do what we call rationalizing the denominator. So we multiply the top and the bottom by square root of 14, okay, over square root of 14. And that's multiplying by 1, so it doesn't change the value of our answer. It just changes the form. Okay, it's like swapping a quarter for 2 dimes and a nickel. Okay, so then we have on the top negative 5 times the square root of 14. And on the bottom, we have square root of 14 times square root of 14 is the square root of 196, which is 14. Okay? And so this answer and this answer are the same, it's just a different format. Okay? Now, that's what there is to adding and subtracting radicals.